Whoa. That's a little wild. All right. So today is our review day for the second test, guys, and we can work on whatever it is you guys would like to work on. There's a few things that I kind of want to go over, sort of discuss some strategies and special limits that you may want to use. But beyond that, the problems we solve are up to you. So I'd like to get started by showing you a handful of special limits. Some of these you may have encountered in the homework. So without further ado, let's get the doc cam going. The sections on the test, pretty sure everybody knows, but just because we always do this, there's 7.8, 11.1, 11.2, 11.3, 11.4, 11.5, 11.6, and technically 11.7. Although 11.7 doesn't have anything fresh in it. 11.7 is just an amalgamation of problems from 11.2 through 11.6. This is called strategy for testing series. And one of the things I want to discuss with you guys today is a little bit of this section of the book, which might help you. 11.6 is on the root and ratio tests. And the concept of absolute convergence. Okay, Kat. Okay, you don't want breakfast, go. 11.5 is on alternating series. Specifically the alternating series test and the estimation theorem. People often ask me, should I expect to use every single test on the exam? Not necessarily, but I would expect to use the estimation theorem at least once. 11.4, these are the comparison tests. .3 was the integral test. 11.2 is just the definition of series, as well as geometric and telescoping series. And then 11.1, this was on sequences. And 7.8 was improper integrals. So I call this test the convergence test, right? This exam 2 is the convergence part of the course, because this is where I test you on all of the different convergence things in the class. After exam 2, we're going to talk about power series a little bit, which are still series, so we're going to be staying in series land somewhat, but the focus will shift a little bit less from convergence towards talking about how to represent functions as power series. And it's not easy stuff, that's still challenging stuff. But if you get your head all the way around these concepts, then those won't be very hard. And after we finish power series, we are going to shift back to stuff that has nothing to do with series. We're going to talk about some applications, some things that are generally considered easier. All right, before we start solving problems, and feel free to start typing problem numbers into the chat that you want to see solved today. But before we get to solving those, I want to show you a couple things. First, special limits, which you can freely use. On the exam. What I mean by freely use is you don't need to explain these particular limits, right? So you need to show work for all of your problems. But if you bump into one of these limits, you're allowed to just write it down. In other words, you're welcome to memorize these. You don't have to, of course, but it's my recommendation that you remember them. So the first special limit, this shows up often enough in the root test. It's the limit as n goes to infinity of the nth root of n, which is also the limit as n goes to infinity of n to the 1 over nth power. Strictly speaking, this is an indeterminate form, infinity to the 0. This guy is 1. And the calculation of this limit requires using L'Hopital's rule. You would take natural logs, and then bring the power down, and then use L'Hopital's rule. But you're allowed to just tell me that the nth root of n goes to 1. The other special limit involves the number e. If you see something of this form, which is equivalent to like this, which is an indeterminate form of the type 1 to the infinity rather than infinity to the 0. This goes to e to the a times b. And I strongly suggest that you prove these. As an exercise. So you remember them. Both of them are indeterminate powers. So both of them require taking natural logs, manipulating algebraically, and applying L'Hopital's rule. They're both pretty time consuming. So I don't recommend, every time you bump into one of these on the test, taking the time to burn through it slowly. I think it is wise to remember what these look like and then just make use of them. And the best way to remember what these look like is to go through the process of proving them. So yeah, that is what I wanted to show you before we dive in. The only other thing I wanted to show you was something from the textbook. One, there is indeed, the n to the n and n factorial. I think the one I put in your homework is n factorial over n to the n series. Definitely leads to something like this. And then there's lots of opportunities for you to bump into something like this anywhere you choose to use the ratio test, the root test on a series that has a factor of n. So one more thing before we get to explicit problem solving. And that is this, section 11.7 in the textbook. I would recommend reading this. All right, I'm going to go through it with you right now, and you can take notes as we do. But I would recommend coming through and reading this on your own as well. So section 11.7 is a lot like section 7.5. You remember section 7.5 just before exam 1? We didn't have any homework from that section because there wasn't anything new in it. But I took a bunch of your study guide problems from 7.5 because it has a mixture of all the integral problems from 7.1 through 7.4. 11.7 is the same thing, but for series. You haven't had any homework from it because it doesn't have any new content. But a lot of your study guide problems came from here because it has a mixture of problems from 11.2 through 11.6. The neat thing about this section is that they have a little discussion here suggesting an order that you choose your convergence tests. So first things first, you need to remember the difference between a sequence and a series. All of this shit only applies to series. Sequence is totally different. All right, a sequence converges if it has a limit. So if I'm only asking you about a sequence, then you don't need to do any of these convergence tests. You just need to remember the content from 11.1. But if you are handed a series and you don't know what to do, consider going through the following steps. First, check if the thing is a p-series. Is the series of the form sigma 1 over n to the p? If it is, then it's a p-series, and you just say whether p is bigger than 1 or not. If p is bigger than 1, the series converges, otherwise the series diverges. If the thing ain't a p-series, you check, is it sigma some constant times some other constant to the n or n minus 1? Is it geometric? Is there a common ratio? If yes, write down the common ratio, check to see whether its absolute value is less than 1. If it is, the series converges, otherwise the series diverges. And you know how to figure out the sum using that formula, starting term over 1 minus r. It's also possible that your series is telescoping, and I recommend at this stage kind of asking yourself, could this be a telescoping series? Does it look like something I could do partial fractions on? All right, if the series kind of looks like a p-series or kind of looks like a geometric series, but isn't actually one of those, like maybe there's a +1 somewhere, or there's something else going on that messes up it being geometric or messes up it being a p-series, you might be able to use a comparison test. If you're able to build an inequality in the obvious direction, then you can use a direct comparison test. If you can't build an inequality, but you're still thinking this thing looks a lot like some p-series or looks a lot like some geometric series, then you should use a limit comparison. So I would read this whole paragraph, but if your series is not geometric, not a p-series, and you don't think it telescopes, then you should consider some sort of comparison test. Remember that comparison tests only work on series with positive terms. So just like the problem we worked yesterday in class with the sine of n over n squared, you may have to take absolute values first and then check for absolute convergence in order to use a comparison test. All right, if it's not a p-series, it's not a geometric series, it's not a telescoping series, and you don't see an obvious comparison, you might take a second to run the test for divergence. It's not hard to run the test for divergence. You should always just run it in your head. I say, take the limit of the ANs in your head. Only write it down if the limit of the ANs isn't 0. If the limit of the ANs is 0, then we don't learn shit, and there's no point in writing anything down. But if the limit of the ANs isn't 0, right, you do that limit in your head. If the limit isn't 0, then go ahead and write it down, and you can conclude that the series diverges. If the series happens to be an alternating series, use the alternating series test. There's no harm in that. If you think that the series might converge conditionally, that is, if you took away the -1 to the n, then you can come back to step 3 here and maybe take absolute values and do a comparison test. But if you think that the convergence is conditional, if taking away the -1 to the n would kill the convergence, then you should use AST. Use the alternating series test. If the series has factorials in it, or other things that look like factorials, consider using the ratio test. And remember that if the series is a rational function of n, like certainly 1 over n, but also n plus 5 over n squared, that stuff, remember that the root and ratio tests don't give a shit about those things. If the series has a bunch of non-constant stuff raised to the n, you should use the root test. And then finally, only in last resort situations, if the series is made up of something where if you swap the n's for x's, you get a function you know how to integrate easily, then you can consider using the integral test. So again, I recommend the tests be done in the order they're presented here. Of course, if one of these jumps out at you like, oh, this has factorials, go straight to the ratio test. But if you have absolutely no idea what to do, then I would run through them in the order presented here. So specifically thinking of the integral test as last and checking for p-series, geometric, telescoping, and comparisons first. All right. So we want to see 11 and 16 on homework 6, 17 on homework 9. So let's go back to homework 6. Sorry, you can see I fell down a YouTube rabbit hole yesterday. Let's push it. Okay. So number 11 here. Oh, we've done this one a few times. I'll do it quickly. We want to integrate from negative infinity up to 0, the function z over z to the 4 plus 16 dz. And as with all improper integrals, the place to get started is by writing this as a limit. This is the limit. I like to use the symbol capital R, goes to negative infinity, integral r to 0, z over, I'm going to write z to the 4 as z squared squared plus 16 dz. So I really did two things at once there. I wrote it as a limit, but I also recognize z to the 4 as z squared squared. And I did that because I'm thinking about a substitution. The numerator there is just z, which means I couldn't substitute for the whole denominator. The derivative of the whole denominator is 4z cubed. And I don't have a z cubed upstairs to play with in terms of the differential, but I do have a z upstairs to play with in terms of the differential. So if I make the substitution, w equals z squared, then dw is 2z dz. And I do have a z dz here that I can play with. I would also change the bounds. When z is equal to r, w will be equal to r squared. And when z is equal to 0, w will be equal to 0 squared, which is still 0. So I'll get lim r to negative infinity, integral r squared to 0. Z dz is 1/2 dw, and then the rest is 1 over w squared plus 16. So this is what my integral looks like after that substitution. We can pop out the 1/2. And it can come out all the way past the limit. And 16 is the square of 4. From here, you have a choice. If you did as I suggested before exam 1 and proved the formula for the integral of 1 over x squared plus a squared, you can at this stage just write down your antiderivative. If you have not proved that formula, or you do not remember that formula, then from here you would make the substitution w equals 4 tangent theta. It would be a trig sub thing. But if you have remembered that formula, and I'm going to operate here as though you have, I'll write down the formula. Integral 1 over x squared plus a squared dx. This is 1 over a times the inverse tangent of x over a plus a constant. Integrals like this show up often enough that I think it's worth remembering that. Then you get 1/2 limit r to negative infinity, and then your antiderivative here would be 1/4 inverse tangent w over 4. And we need to evaluate this from r squared to 0. So now I'll evaluate between bounds. I can pop this 1/4 all the way out. I'll get 1/8 limit r to negative infinity inverse tangent of 0 minus the inverse tangent of r squared over 4. The inverse tangent of 0 is 0. And as r goes to negative infinity, if I take this limit, then r squared will be going to positive infinity. So this piece will be going to the inverse tangent of positive infinity over 4. Positive infinity over 4 is still positive infinity. So maybe I'll do like the limit infinity logic stuff over here. All right, as r goes to negative infinity, r squared over 4 is going to go to positive infinity. That's the upshot. So this piece, the inverse tangent of r squared over 4, is going to go to pi over 2. So I end up with 1/8 0 minus pi over 2. And that's going to be a negative pi over 16. In particular, this integral converges. We would say converges to negative pi over 16. So that's the result. That was number 11 from homework 6. There will be at least one improper integral on the test. All right, that's just for its own sake, evaluate this improper integral. It's important that you remember to write these as limits. It's your very first step, is to rewrite the integral as a limit of a proper integral. And then everything between there and the end is like test 1 stuff, just figuring out how to get to an antiderivative. And then at the very end, we come in and we take the limit. Think of this as like the partial sum. So the full infinite series is the limit of the partial sums, just like in 11.2 when we're talking about series. There's a deep connection there between integrals and series that we explored in the integral test. To be efficient with time, I'm just going to move to number 16. So here they just ask us whether the integral converges. Oh, no, and then they said if it converges, evaluate it. Okay. This is a type 2 improper integral. I'm going to ignore the 51. I'm just going to say this is 1 over the square root of 1 minus x squared. So does this integral converge or diverge? If it converges, find the value. Where is the problem? Is the problem at 0? Is the problem at 1? Is the problem somewhere in between? Good, yeah, the problem's at 1. As x tends to 1, this piece becomes the square root of 0, which is 0. So you get a 1 over 0. So this function blows up, or at least might blow up at 1. So I would write this as the limit as r goes to 1 from the left, integral 0 to r, 1 over the square root of 1 minus x squared dx. And now this is actually similar to the previous one in the sense that if you know your inverse trig stuff well, you can do the integral itself very fast. The antiderivative here is just the inverse sine function. Right? This is 1 over the square root of 1 minus x squared is the derivative of arcsine. And that is something that we should know. So we get sine inverse of x between 0 and r. Now, if you don't remember the derivative of the inverse sine function, then the move here would be to make the substitution x equals sine theta, following your trig sub-Bible. But hopefully you do remember the derivative of the inverse sine function. It's something we talked about in this class and you learned back in Calc 1 as well. So now it's just a matter of crunching out this limit. What is the limit as r goes to 1 from the left of the inverse sine of r? And we have to subtract off the inverse sine of 0. The inverse sine of 0 is 0 because the sine of 0 is 0. But to sort out the limit as r goes to 1 from the left of the inverse sine of r, you need to be thinking about the arcsine function, the inverse sine function. Fortunately, the inverse sine function is actually continuous at 1. Right? There's no need to really futz about with limits here. This is just sine inverse of 1 minus 0. And sine inverse of 1 is what? Very good, pi over 2. Right, because the sine of pi over 2 is 1, and pi over 2 is between negative pi over 2 and positive pi over 2. If you don't remember the graph of the inverse sine function, the graph of the arcsine function looks like this. It has vertical tangents at -1 and +1, but it is continuous there, or at least left and right continuous. So as x tends to 1 from the left, the inverse sine of x does tend to pi over 2. Okay. So this one, not too bad. Both of these could be made worse if you don't remember your inverse trig stuff. In both of these, you would need to do a trigonometric substitution if you didn't remember the inverse trig results. Here again, the substitution would have been x equals sine theta because you have a 1 minus x squared under a square root. All right, we're going to jump to Maggie's next question, which is number 17 on homework 9. If anybody else has questions, I do want you guys to ask them, please. I know that this material is intimidating, so I would be shocked if nobody else had any questions. One mentions something similar to one of our special limits on homework 9. Is that a problem you wanted to see worked out, one? Oh, okay. All right. Oh yeah, well the n factorial over n to the n, this was that problem. So this is the one that, yeah, nice, okay. Yeah, this works nicely. And I think 18 would be a good choice also because this is a strange factorial-like product in the numerator. All right. Yeah, convenient choice there. Teamwork makes the dream work. So homework 9, number 17. We want to investigate the convergence of the series. And I'm going to give it the name S so I can refer back to it conveniently. Sigma 1 to infinity n factorial over n to the n. So I see a factorial, and I also see a bunch of stuff raised to the nth power. The top here kind of hints at a ratio test. The bottom here kind of hints at a root test. But taking the nth root of n factorial, that's hard, like hella hard. We don't want to do that. So I'm going to use the ratio test. And I think the problem suggests the ratio test. But if it doesn't, then the n factorial certainly does suggest the ratio test. Now on your exam, I recommend writing down the recipe here explicitly. Start by writing this. L equals the limit, absolute value, an plus 1 over an. Or for whatever test you're using, start by writing out whatever formula the test calls for. That way, even if you goof up, I can give you some credit for having remembered how the test is supposed to work, right? Like maybe I can give you a half point or maybe even a full point for remembering, oh yeah, the ratio test says you start by calculating this limit. We need to figure out what an plus 1 is. An is n factorial over n to the n. So to get an plus 1, I swap all the n's for n plus 1's. That's going to be n plus 1 factorial over n plus 1 raised to the n plus 1. The most common mistake I see at the early stages of this problem is forgetting this n plus 1 right here. So I'm going to divide this by this. Good, good. Oh, I see. You're saying you forgot that. Yeah, okay, no, yeah. Common error, common error. Also, common error is forgetting parentheses here. N plus 1 factorial is not the same as n factorial plus 1. So we're going to divide an plus 1 by an, and then we're going to run into a pretty tricky limit. Okay, so continuing to calculate L, this is the limit as n goes to infinity of the absolute value of n plus 1 factorial divided by n plus 1 raised to the n plus 1. And then rather than dividing by an, I'm going to multiply by its reciprocal. So that's n to the n over n factorial. I'm just going to jump straight to that because we know that would be the next step. So here's an plus 1, and instead of dividing by an, I multiply by 1 over an because an is a fraction. And that would be our first step after dividing like that. I'm going to group the factorial terms together and the n to the n terms together. Or maybe even before then, let's see. Everything here is positive, so I can forget the absolute values. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. That's what n plus 1 factorial looks like. It's the product of all the positive integers less than or equal to n plus 1. So the factorial of anything you get by starting with that thing, then that thing minus 1, then that thing minus 2, all the way down to 1 times. N to the n is just n to the n. N plus 1 to the n plus 1 is n plus 1 times n plus 1 to the n. So I'm using this rule for powers that says n plus 1 to the n plus 1 is n plus 1 to the 1 times n plus 1 to the n. And then I'll write out n factorial. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And what you see is a lot of cancellation in the factorials. N plus 1 factorial has a copy of n factorial inside of it. So they cancel. And then the n plus 1 from n plus 1 factorial cancels with the n plus 1 from n plus 1 to the n plus 1. So the two terms which survive are these. I'll have n to the n over n plus 1 to the n. And I'd like you to take a second and think about what happened with the factorials there. One of the results that sometimes I see students remember is that n plus 1 factorial being n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1 is the same as n plus 1 times, what is this? This is n factorial. And in general, if m is bigger than n, then m factorial contains a copy of n factorial. For example, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. This has a copy of 4 factorial in it right here. It also has a copy of 5 factorial in it right here. It also has a copy of 6 factorial in it right here. All right, so I'll emphasize here the copy of 6 factorial. But we could have said, you know, I'll take these last 5 terms, that's 5 factorial, or just these last 4 terms, that's 4 factorial. So if you have a bigger number, the factorial of the bigger number will contain a copy of the factorial of the smaller number. It's a useful fact. You can actually take this to be the definition of the factorial function. When we first discovered the factorial function, we treated it as a recursive sequence following this recursion relation. So the simplest form of this fact can be stated like that. And then you can recurse down to get out whatever you need. But my preferred attack here is just what we did here. Just write the things out. Just remember what the factorial is. It's the product of that number with the number below it with the number below it until you get down to 1. As long as you remember that, you'll be safe. Just got to take your time and write things out. Now I'm left with this. As n goes to infinity, the top there is infinity to the infinity. That's definitely infinity. And the bottom is also infinity to the infinity. So this looks like infinity over infinity, which is an indeterminate form. So I don't know what this looks like yet. And what's more, it's very hard to apply L'Hopital's rule directly to this limit. Does anybody remember even how to differentiate n to the n or x to the x? Think back to the middle of your Calc 1 class. The power rule doesn't work. It's not n times n to the n minus 1. Why doesn't the power rule work? Well, the power rule only applies to things with constant powers, and this isn't a constant power. You also can't differentiate it as an exponential. Like the derivative of n to the n is not n to the n times the natural log of n, as you would use if this was a constant, because the base isn't constant. So the derivative of the top here is actually a complicated expression that requires logarithmic differentiation to calculate, just like the derivative of x to the x is complicated. So rather than attempting L'Hopital's rule at this stage, the move here is to just do some algebra. The top and bottom are both being raised to the n, so this is the same as n over n plus 1 to the n. Which is still an indeterminate form. The inside is now going to 1, so this is an indeterminate form of the type 1 to the infinity. And you got to think to where else you've seen that. You've seen that today when I described that special e to the ab limit. So we want to kind of massage this until it looks like 1 plus a over n all to the bn power. And the fastest way to do this is to rewrite it as n plus 1 over n to the negative n. Flip the inside, the power becomes negative. Now inside here, I can split up this fraction. N over n is 1 plus 1 over n all to the negative n power. This is one of your e to the ab limits. A is 1, and b is negative 1. So this limit is e to the negative 1, or 1 over e, which is less than 1. Which tells me that the series in question not only converges, but converges absolutely by the ratio test. So this is a tricky problem. I'm not going to pretend like this is a super easy problem. It's not. There's places to make little algebra mistakes, and even if you do everything perfectly and you get to this step, this limit is still quite hard. questions on what we did here? If you don't happen to remember that special e to the AB limit, then once you get to this stage, you could take the natural log and then attack it with L'Hopital's rule, the same way you attacked indeterminate powers with L'Hopital's rule in Calc 1. But it takes a lot of time. So this would be a fair homework question, but it's a little tough for a test question unless I give you a hint that helps you get more rapidly to here. Now I could give you something that more quickly gets to a limit looking like this and hold you responsible for that on the test. Or I could ask you to cook up this ratio test limit for this function, or for this series, and get it to this point, and then give you a little hint. And I expect you guys to be able to, in particular, navigate the factorial cancellation here. That's a little bit tricky. Okay, so Juan wanted to see number 18 from the same homework set, and then we're going to go back to homework 8 and look at Zach's question, problem 15. So let me do 18 here. This is a good problem. You've got the sum from 1 to infinity of 6 times 12 times 18 up to 6n all over n factorial. Same business, investigate the convergence. The sum here is taken from 1 to infinity, and the numerator is 3 times 6 times, what was it? Was it? No, 6. Yeah, just 6. 6 times 12 times 18 all the way up to 6n divided by n factorial. All right, this one can actually be done very quickly if you're clever. I think the problem suggests that you use the ratio test, and indeed, we've got a bunch of stuff that looks like factorials here. But I just want to play with that product in the numerator. I think it's illustrative to write out the first few terms here. So what's the first term of this series? If I plug in n equals 1, what does this product look like when n is equal to 1? Good, it's just 6, right? The first term in the product here is supposed to be 6. It's 6 times 1 times 6 times 2 times 6 times 3 times all the way out to 6 times n. But if n is 1, then 6 times n is 6. So there's just one term in this product if n is equal to 1. So this is 6 over 1 factorial plus, if n is equal to 2, that's 6 times 12 over 2 factorial plus, if n is equal to 3, it's 6 times 12 times 18 over 3 factorial plus, if n is equal to 4, then it's 6 times 12 times 18 times 24 over 4 factorial plus, if n is equal to 5, then it would be 6 times 12 times 18 times 24 times 30 over 5 factorial, and so on. I know that you guys have a hard time often interpreting these sort of products. So when you see something like this, please do me and yourself the favor of writing out the first few terms to check and make sure you understand what that product is and to demonstrate to me that you know what's going on there. All right, here's the fast solution. AN is 6 times 12 times 18 all the way up to 6n over n factorial, which is 6 times 1 times 6 times 2 times 6 times 3 times all the way up to 6 times n over n factorial. So the 6 is here, everything is being multiplied. Everything is being multiplied. So there's 6, you can reorder the multiplication. This is 6 times 6 times 6 times 6, n times, all times 1 times 2 times 3. So if I multiply 6 by itself n times, what is that? Yeah, good, 6 to the n. And what is the product 1 times 2 times 3 all the way up to n? Ooh, shit, I messed it up. Yeah, 6 to the n. Okay, and then what is the product 1 times 2 times 3 all the way up to n? Yeah, that's n factorial. So the numerator here is really 6 to the n times n factorial. So this is, an here is 6 to the n times n factorial over n factorial. You can cancel the n factorials. This series is actually geometric. It's geometric with common ratio 6. And this is by far the fastest way to solve this problem. I'll write it out. This is a geometric series with r equal to 6. So the absolute value of r is 6, which is certainly bigger than 1. So the series diverges. Okay. So just by writing out the terms of the series and thinking about ways you could rewrite that product in the numerator as 6 times 6 times 6 n times 1 times 2 times 3 times 4 all the way up to n, you realize you've got a copy of n factorial upstairs and downstairs. You can cancel those, and the thing you're adding up is really just 6 to the n, which is a divergent geometric series because the common ratio is certainly larger than 1. The intended solution here is the ratio test. And because I think it's important to practice with factorials and factorial-like products, I will quickly run through that. L is the limit as n goes to infinity, absolute value, an plus 1 over an. Here, again, I think the challenge is in getting an plus 1 right. An plus 1 is 6 times 12 times 18 out to 6n. And then the next term would be 6 times parentheses n plus 1. And then downstairs we have n plus 1 factorial. This apparatus right here is an plus 1. By writing the second to last term and the last term in this product in the numerator, it makes it easier to see what's going on, and it will make it easier to see the cancellation. You may have noticed every time I write a factorial, when I go to write out a factorial, I write the first few terms and the last few terms. I don't just write the last term at the end, and I don't just write the first term at the start. Like n plus 1 factorial, I write n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. I write several terms at the end and several terms at the top. By doing the same thing here, by writing the first few terms at the start, and then not just the last term, right? If you just swap n for n plus 1 in this expression, you wouldn't see the 6n right before. But I know what this product looks like. It's all the multiples of 6 up to whatever it tells me to stop at. So an plus 1 is going to be all the multiples of 6 up to the n plus first multiple of 6, which means the second to last term is the nth multiple of 6. And it's really useful to write not just the first few, but also the last few terms. And then remember, n plus 1 is always in parentheses when we do this. So the bottom is not n factorial plus 1, it's the factorial of n plus 1. And the last term in this product is not 6 times n plus 1, it's 6 times parentheses n plus 1. So this is an plus 1. And then an, I need to divide by an, so that would be multiplying by n factorial over 6 times 12 times 18 all the way up to 6n. And this is all in absolute values. Having written the product carefully in this way, the cancellation is pretty obvious. And I get lim n to infinity. N factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. I still have my 6 times n plus 1 upstairs. And then downstairs, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. The n plus 1s here cancel. The remaining pieces of the factorial cancel. And I'm just left with the constant 6. The absolute values can go away because everything here is positive. So I get limit n to infinity of 6, which is definitely just 6, which is bigger than 1, so the series diverges by the ratio test. So 2 different solutions to the same problem. The suggested solution is this one with the ratio test. My preferred solution is this one, just realizing that the series is actually geometric. But either one is fine. Okay. So that was 18 from homework 9. We wanted to see 15 from homework 8. And also we're going to try to get to 14 from homework 7. So let me go to homework 8. One requested that first. Here we're given sigma n to the 6, e to the minus n to the 7. Write it down. Summing from 1 to infinity. And they tell us to use the integral test. To investigate the convergence. All right. So we're using integral test. Unfortunately, that means we have to show that the corresponding function, which is f of x equals x to the 6, e to the negative x to the 7, is positive, continuous, and decreasing, hopefully on the interval 1 to infinity. A quick note. It is sufficient to prove that the function is positive, continuous, and decreasing, not necessarily on this whole interval,
but from somewhere to infinity. So if you're not decreasing until like x equals 5, but then you are decreasing everywhere after that, that's okay. Because remember, I don't really care about what happens in the first 10 terms of this series. I only care about the tail. But if we're lucky, we'll be able to get the exact form that we had in the theorem. So positivity, f of x is greater than 0. Well, that means x to the 6 times e to the negative x to the 7 is greater than 0. Exponentials are always positive. So this is true as long as x to the 6 is greater than 0. And x to the 6, that's an even powered power function. This is also true for all x not exactly equal to 0. And in particular, it is true on the interval 1 to infinity. So we are happy with this. Second fella, we want to show that this is continuous. Well, f of x is x to the 6 times e to the negative x to the 7. This is a product of a polynomial and an exponential, both of which are continuous everywhere. So the product of two continuous functions is indeed continuous. So we got nothing to worry about here. The work shows up in verifying that this is decreasing. So if you take the function x to the 6, e to the negative x to the 7 has derivative f primed equal to, I now need a combination of the product and chain rules. The derivative of x to the 6 is 6x to the 5. So I have 6x to the 5 times e to the negative x to the 7. Plus, now I'll leave the x to the 6 alone and differentiate e to the negative x to the 7. That will give me e to the negative x to the 7 times, by the chain rule, negative 7x to the 6. What a mess. I can factor out e to the negative x to the 7. And that piece is always positive, so I don't need to stress about him. What will be left is 6x to the 5 minus 7 times x to the 6, x to the 6, that's x to the 12. And then I can factor out an x to the 5. So this is x to the 5 times e to the negative x to the 7 times what remains here is 6 minus 7x to the, what is 12 minus 5? 7? So x to the 5 is greater than 0 on 1 to infinity. E to the negative x to the 7 is greater than 0 everywhere. So f primed of x will be less than 0 if and only if the bracketed stuff is less than 0. 6 minus 7x to the 7 is less than 0. 6 minus 7x to the 7, that's a polynomial with an odd degree and a negative lead coefficient. So its end behavior is down on the right and up on the left. It has one root that we can calculate nicely. This is equal to 0 when 6 is equal to 7x to the 7. That happens when x is equal to the 7th root of 6 over 7. So f primed is less than 0 for all x greater than the 7th root of 6/7, which is smaller than 1. Hence, f is decreasing everywhere on the interval 1 to infinity, which is what we wanted. I did this as efficiently as possible. Let me be clear. If you kind of stumble through this shit, it will take forever. Forever. Not a fun process. Not at all fun. So I've said it before, I'll say it again, fuck the integral test. Fuck the integral test because this shit takes forever. But it works. We're happy. So now that we've proven these three things, we know that the integral test applies. And that means the integral will converge if and only if the series converges. So we compute the integral. The integral from 1 to infinity, x to the 6, e to the negative x to the 7 dx. This is not very hard. It's the limit as r goes to infinity, integral 1 to r, x to the 6, e to the negative x to the 7 dx. And we do this by making a substitution, z equals x to the 7, dz is 7x to the 6 dx. Our bounds change. 1 goes to 1, and r goes to r to the 7. And we get limit r to infinity. I'll have a 1/7 pop out from my differential, all right? Because I've got an x to the 6 dx here, and 7x to the 6 is dz. So 1/7 dz is the x to the 6 dx. My integral now goes from 1 to r to the 7, and I'll have e to the negative z dz. Whose antiderivative is negative e to the negative z. This is my 1/7 out front. And we evaluate this from 1 to r to the 7. So this is going to be, I'll do it down here, lim r to infinity. (1/7) times negative e to the negative r to the 7 minus negative e to the negative 1. Now as r goes to infinity, r to the 7 goes to infinity. So I get 1/7 negative e to the negative infinity plus e to the negative 1. And e to the negative infinity is 0. So this is 1/7 0 plus e to the negative 1, or 7 over e, which is finite. So the integral converges. Thus, by the integral test, the series converges also. What was it? N to the 6 e to the negative n to the 7. That series must also converge. Oh, it is 1/7 e. Thank you, thank you, thank you, thank you. Yeah, the 7 was downstairs, right? Sorry, so this is 1/7 e. Yeah, good eye. Thank you. Okay. Yeah, so these integral test problems take forever. They're not pleasant things to do. They would be pleasant, except the process of showing that the function is decreasing can sometimes take forever, can be really unpleasant. The rest of it isn't too bad, right? Computing the integral isn't too bad. Positivity and continuity aren't too bad. And sometimes you can get away with an easy argument for decreasing. Remember, the 3 ways to show that something is decreasing are to show that the derivative is negative, or state that it is the reciprocal of an increasing function, or to show that the inequality defining the term decreasing is satisfied. The inequality is usually the hardest way. I want to say that, right? Because I see a lot of times in homework and stuff, students like to show that bn plus 1 is less than bn, and usually they just state it. They just say that bn plus 1 is less than bn without any justification. I want to be clear that that's not sufficient. If you're going to use the inequality to show that something is decreasing, you need to prove that inequality, and that's usually hard work. So my advice is to avoid that. Either do the derivative thing like we did here, or observe that your function or sequence is the reciprocal of an increasing one. Here we couldn't get away with that because our function is not the reciprocal of an increasing function. We had to do the derivative thing, but doing the inequality work would have been even harder. We have time for one more if we do it quickly. And I think Antoine Tanji had a question here. Yeah, number 14 from homework 7. So let me get quickly to that. Good, a sequence problem. I'm glad somebody asked one of these. Bad, I'm out of paper. All right, this last one. You're gonna see me work on a folder because I want to get to it. It's the nth root of 4 to the 4 plus 3n. And we want to know, does the sequence an converge? What does it mean to say a sequence converges? This is not a series now, this is a sequence. What's the difference between a sequence and a series? And what does it mean to say a sequence converges? Nick, before you go, you want to clue us in on that? No? Anybody? Remember, a series converges if its sequence of partial sums converges, or equivalently, if when you add up all the terms, you get a finite number. Yeah, sequences are much simple. A sequence converges if it has a finite limit. So we need to take the limit as n goes to infinity of the ans. That's all you need to do for sequences. Not sufficient for series, but is sufficient for sequences. So that's the limit. I'm going to rewrite this as a power. That's 4 raised to the 4 plus 3n, all raised to the 1 over nth power. And now we can do some algebra. This is the limit as n goes to infinity of 4 to the 4 times 4 to the 3n, all raised to the 1 over nth power. All right, adding in the exponent is the same as multiplying like bases with those exponents. And then I can give that 1 over nth power to each of those pieces. This is 4 to the 4 times 1 over n times 4 to the 3n times 1 over n. And this is multiplication. In the second piece, the n's cancel. So here I'll have 4 raised to the power of 4 over n, that's the first piece, times 4 raised to the 3n times 1 over n, that's just 4 raised to the 3. So this is 4 raised to the 0, as n goes to infinity, 4 over n goes to 0, times 4 to the 3. And 4 to the 0 is 1, so this is 1 times 4 cubed. 4 cubed is 64. So that is it. That is the limit of this sequence, since lim n to infinity an exists and is finite, it's 64. The sequence an converges to 64. Not too bad.
Good morning, sir.
I know that you guys have a lot of homework to do, and I've heard surprisingly little from y'all, which makes me think that, well, maybe we haven't worked as much on this stuff as we should. I know that at this point in the semester, a certain amount of malaise can kind of kick in. You get a little bit complacent and a little bit bored and a little bit tired. But I want to remind you that this stuff is not boring. It is tiring, but it's not boring. It's very, very hard. And also, after exam 2, we are going to continue working with series. We're going to be working with power series, but we're going to continue working with series. Now, there won't be this big issue of what convergence test do I use. The question is going to be very different. It's going to be, how do I represent this function as a power series? Totally different game. We're only going to do that for a few weeks, and then we're going to switch to talking about other stuff, application problems. The application problems I think you'll find quite easy, but the power series I think you'll find quite difficult. If you want an office hour over the weekend, we can try. Send me an email or a Canvas message, and I'll do my best to set up at least one that fits as many people's desires as possible. Both of my Calc 2 sections and my Calc 1 section have an exam on Monday, so I'm expecting to be a little bit swamped with requests, so I might not be able to meet every request. But if you send me your request soon, just give me the day and the time you want to meet, maybe give me a few times, I will do my best to accommodate as many people as possible. One last thing, this afternoon my wife has an ultrasound, so we're going to be at the doctor from like 1 to 3 or something like that. So I won't be able to do my normal office hour at my normal time this afternoon. I'll have to reschedule this afternoon's office hour for a later time, kind of like what we did yesterday, where I had to go vote and came back and then did an office hour after that. I'll be doing something similar today. So as soon as we get back from the doctor, I will post an announcement letting you know when today's office hour is. It's not going to be at the normal time. And then if you want an extra office hour over the weekend, send me a message giving me a list of like 3 or 4 times that would work well for you. Do that as soon as you can, and I will do my best to accommodate as many people as I can. All right, keep working hard. Do the homework first, then the study guide. Once you finish the study guide or get stuck on a problem on the study guide, send me a photo of your work. I will give you some feedback as though it is an exam question, and we can move forwards from there. Prepare hard, and this will be okay. Slack, and this will go badly, I promise. So I want you guys to do well, prepare hard. I'll do my best to help you get through this, and I'll see you guys either in office hours, or if not in office hours, then I'll see you guys next Wednesday. Take care.